The other thing on Friday is, again, we've had 2 snow days. So as you know from your original schedule, we were supposed to use 2 days for quizzes. So again, Caitlin and I are obligated so we don't lose any class time. I know you're going to be very disappointed, but on Friday, you'll be receiving quiz number 2, and it will be a take-home. And that take-home will be due. Your schedule tells you when it's due. It's due on Monday. Okay, so Friday you'll get your take home, and I'm going to make this clear now so that I don't get anybody calling me. If you are not in class, I'm going to write it down. If you are not in class on Friday, don't write me and say, send me my take-home quiz. It works the same way. If you were not here the day a quiz was being given, you wouldn't be able to take the quiz. So if you're not in class on Friday, then don't send me an email asking for me to send the quiz to you. Okay? If you're not here, it's just like if you were in here for a quiz or a test. It's a 0. But I know you're all going to be here. All right. So today we start to deal with numbers outside of the real number system. As you recall, our real numbers exist on a real number line. They have a home on this number line. And they break out into 2 groups that have no common elements. Their intersection is empty. If you're a real number, you're either rational, which means you'd be expressed as A over B, or it means as a decimal, you have a number or a set of numbers that repeats, or you terminate, like 7 is 7.0, it terminates. Has nothing that repeats, so you could say it repeats 0 if you want to think of it that way. Or you're irrational, which means you can't be expressed as the division of 2 numbers, A over B. So now we're going outside of that. We're going to expand our number set, and we're going to deal with the idea of complex numbers. Okay? And so Caitlin and I are just going to give you this definition. It's not something that's like you can feel inside your soul. It's not concrete. You can't hold the square root of -1. Okay? It's a definition. Just like if you don't know what the word Schadenfreude means, you would look it up and you would look at the definition. I had to look up that word once. Okay? So mathematicians define I. They use the symbol I to represent the square root of -1. That's the definition. So for our purposes in this class, we will be using I, but we also will be using a power of I. If I were to square both sides, can anybody tell me what the right side of this would simplify to? The square root of -1 squared. What would that be? -1. Because remember, the square root and the square are inverse operations. They undo each other. If I had the square root of 9 and I squared it, I'd have 9. Okay, so these undo each other. So I square is equal to -1. So these are really the 2 facts that you're going to be working with most in this class. Is this I square is the same as the number -1, and I is the square root of -1. So one of my former 107 students sent me this cartoon the other day, and I thought it was really perfect for this class. I'm glad she sent it to me. I thought that was kind of cute. So here's the poor square root of -1 saying, "Do I really exist?" I thought it was funny. Anyway, so she has a good sense of humor. She has gone on to Mount Holyoke as a math major. So interesting. And it all began at GCC. Anyway, so let's suppose we had a number under a radical sign that wasn't -1, but it was a negative number. Well, up to now you would say, no can do. I can't take that square root of a negative number because it's not a real number. Well, now we have these numbers called complex numbers that we use this little I to help us form, and we'll get there in a minute. So if you see something like the square root of -49, all you do is you break it up into 2 factors, where one of them is your -1. And if I pull a negative, if I divide this by -1, what's left is 49. And now you can write what each one of these represents, because the square root of -1 is I, and the square root of 49 is 7. And I times 7 is the same thing as 7 times I. Doesn't matter which order you write it in. It's usually standard to put the real number in front of the I, but it doesn't matter to me. How about square root of -8? What would be my first step here? Can anybody help me with that yet, Moshe? 2 parts, and what would they be? Well, let's do 2 first. -1 and 8. Okay, someone want to help me from there? Sam?
So then you have to keep the root -1.
Root -1, yeah. Root 4 times root 2. Someone want to help me from there? Or help us, I should say. Someone else? Yeah, Doug? I, 2, and root 2. So again, since this is all multiplication, the order doesn't matter, but we tend to do this. 2 times I, root 2. Okay. And we just went over I squared. What's I squared going to be? -1. Okay. All right. So that's just a little bit of work. Let's take this and get rid of it for a minute. Cut. All right. Now let's do some arithmetic with these numbers. Well, if we put I together with some real numbers in this form, A plus BI, where A and B are real numbers. So it could look like this: 2 plus 5I, 3 minus 4I. Notice, if B is 0, 5 plus 0I is just 5. So notice we can say that every complex number, every real number is also complex, because every real number you could just write as that number plus 0I. So the real numbers is a subset of the complex numbers. You can put the real numbers together with imaginary numbers and you become the set of complex numbers. Okay, so this is just the set we're now going to have the tools to use, so that when we solve some equations that we couldn't solve before with real numbers, we now have complex numbers as in our toolkit. All right, so arithmetic, we can do arithmetic with these numbers just like we learned how to do arithmetic with real numbers. And again, the key is remembering that I square is -1. So let's do some adding. Well, these parentheses aren't doing anything. They're just grouping my 2 complex numbers here. So I can just drop those parentheses and I have an addition problem. Nothing changes. Our mathematical systems still work the same way. You can only add and subtract the like pieces. So you have 2 and 1 are your constant real numbers. You add those together, you get 3. And then 3i and 5i becomes 8i. Perfect. Okay, and you're done. 3 plus 8i. Same is true here with subtraction. I can drop my first set of parentheses, but before I drop my second set of parentheses, I have to subtract each one of these terms. So I subtract my 1 and I subtract my 5i, and now I combine my like terms, and I get 1 take away 2i. So with adding and subtracting, it's just like it always has been. Now with this, we have 2 terms times 2 terms. We want to use our distributive property twice. So we do 2 times I is 2. 2 times 5i is 10i. Then 3i times 1 is 3i. And 3i times 5i is 15i squared, right? We can add these 2 terms they're like. We get 2 plus 13i. And then remember, I square is -1. So where you see I square, you can replace it with -1. And so now what we really have is 2 plus 13i minus 15. which is negative 13 plus 13i. So this works exactly the same as real numbers. You just have the little I squared to contend with to simplify this even further. Okay. Yep, you can also write this like this, 13i take away 13. Either one is perfectly okay. They both say exactly the same thing, just the order's different. So however, it works for you, it's fine with me. What do you notice about E? Just the two factors out of there. The first factor is called 2 plus 3i. The next factor is called 2 minus 3i. What do you notice about those factors? Anything? Like if you were going to just, yeah, Marissa? That's right. Remember when we had things like x plus 1 times x minus 1? We would get x squared minus 1 when we were done. The middle term and the outer term cancels when we do our distributive property twice. And so Marissa's saying that, look, if you notice right here, 2 times 3i gives you 6i. Oh, look at this. 2 times negative 3i gives you negative 6i. When you add those two, you just get a 0. So the really fast way of doing this is 2 times 2 is 4. 3i times negative 3i is negative 9i squared. And you are done, almost. Because look, I'm just going to do this in a different color. The middle term here is 6i. And the outer multiplication is negative 6i. And when you add that, you get 0. So if you notice that your two factors are identical, except one is a positive and the other is a negative, then these two multiplications will, when you add them, will be 0. So all you have to do is pay attention to the 2 times the 2 and the 3i times the negative 3i. So why wouldn't I say you finish this off 4 take away 9i squared? Why isn't that finished off? Yeah, because I squared is negative 1. So you can rewrite this. You can simplify it a little teeny bit further by replacing the I squared with a negative 1. And now you get 4 plus 9, which is 13. So isn't that crazy that the number 13 and this multiplication problem are exactly the same? It's like, why make life so complicated, right? I mean, I really prefer to look at 13 than 2 plus 3i and 2 minus 3i. But anyway, it's how it all works. So we have some special names for factors like this. Anytime we see factors where they look identical except for one's addition and one's subtraction, we say that they are conjugates of each other. And you're going to see this a little bit more later on. Conjugates of each other. And so in a more general form, if a plus bi is one number, then its conjugate is a take away bi. And the nice thing is that when we multiply conjugates, we simply have to do a times a for a squared minus b squared I squared. When I multiply these two together. B times b is b squared, I times I is I squared, and plus times negative is negative. And look what happens. A squared plus b squared. So what now you're looking at is a possibility to factor something you've never been able to factor before, and that's the sum of two perfect squares. So before, when you were given something like this to factor, you would say, Linda, I can't factor that. That's prime. You can't factor it with real numbers because if you try x plus 2 times x plus 2, that doesn't work because you'd get x squared plus 4x plus 4. So nothing works. But now it does work. You can do this by saying, what do I square to get x squared? I do x. Now, how do I get the plus 4? You just say plus 2i minus 2i. And you're all done. You factored that. Now with the complex numbers, you've been able to factor that in imaginary numbers. So check it. X times x is x squared. 2i times x is positive 2i times x. Negative 2i times x, and those go to 0. And then we get 2i times negative 2i, which is minus 4i squared. And when you replace that I squared with a negative 1, lo and behold, that subtraction changes to addition. So now you have this ability to factor things you could never factor before. Exciting, woo! I skipped this right here. What's the conjugate of 2 plus 3i? Yeah, 2 minus 3i. We already went over that. Okay. All right, so all of this is leading up to being able to solve a whole category of equations called quadratic equations. So let's take a look at that. Before we do that, let me just quickly go over this with you because we did this in the preview exercises. So one thing you don't want to do here is you don't want to multiply this and call this the square root of 100, because the square root of 100 is 10, and that's not what we're going to get when we simplify this. You want to take each one of these separately. We're going to pull out negative 1 times the square root of 20. We're going to pull out square root of negative 1 times the square root of 5. Square root of negative 1. Now we're going to break 20 up, and a lot of you had practice with this in the preview exercises. That's going to be square root of 4, square root of 5, times square root of negative 1, square root of 5. Okay, this is just one big fat multiplication problem. So what are we going to get when we multiply? Let's simplify these as much as we can. Okay, so I've simplified all of those factors as much as I can. Now, if I group them a little differently, I put the two i's beside each other. Okay, so can anybody help me with that? That looks like just one big giant messy thing to look at, but I think we can do it. What do you think it is? 2i square roots, yeah. So can we simplify 2i square root of 5 times any further? So where'd the negative 1 come from? Let's do it in steps. So I square times 2 and square root of 5 times square root of 5. Square root of 5 times square root of 5 is the square root of 5 squared. The square and the square root undo each other. You get 5. Another way to look at it, if it's not right there for you, is you multiply these. Square root of 25 is 5. Okay, so these two things give us the number 5. 2 times 5 gives us the number 10. And what's I square again? Negative 1, so it's negative 10. So when you're taking the product of two radicals where the number underneath the radical is negative, you want to simplify each one individually. Okay. All right, quadratic equations, here we come. Woohoo! All right, so we say linear equations, which we've been working with and you've been working with a long time, are what we call first degree equations. What the heck does first degree equation mean? Does anybody know? First degree? Well, let's take a look. Quadratic equations are called second degree. So what do you think, Drew? Yeah, the highest degree of the variable throughout the equation. And here, this first example is 1. We don't even bother to put it in. So that's what this first degree means. We call this the degree of your equation, which is the highest power you see. So these are examples of polynomial equations. That's the big category, polynomial equations. We can have things to the third power, fourth power, fifth power, up as big a number as you want, but it can never be a negative number if you're a polynomial. Okay, so that's cool. You don't have to deal with negative exponents or fractional exponents. So these are kind of friendly equations in a way. Okay, and now you see here quadratics, the highest power you see on any one of the variables is the second power. That's why we call it second degree. So in general, this is how we write a quadratic equation. Notice how we use the letters at the beginning of the alphabet, A, B, and C, to represent usually the constants in an equation. And usually the letters at the end are the variables. I mean, they're all variables, but that's just how we use the letters in the alphabet. So A, B, and C are real numbers, and A can't be 0. So when they're given this definition, why do they bother to tell us A can't be 0 anyway. Why do they do that? Drew? You get 0 in the denominator. Yeah, that would really screw us up, right? And what would happen? What kind of equation also, in addition to what Drew said, which is, I actually have never thought of that before, but why would we not want this to be 0? Right, if that was 0, that whole term would disappear, and what kind of equation would I have? First degree or a linear, right. Okay, so there are lots of techniques for solving differential equations. Excuse me, quadratic equations. Okay, let me just tell you one thing. The quadratic formula, which we're going to see, which I know you've heard and seen before, can solve any quadratic equation. So why bother, you say, learning these other techniques? Well, unfortunately, people don't use the quadratic formula with 100% accuracy. So if sometimes you can get away with solving a quadratic equation easily, why not do it? Okay, so I'm going to show you a couple of methods, but recognize you can use whatever method you want, and the quadratic formula works for everything. Okay, the first technique we're going to talk about really has this name for the technique: extraction of roots. There's something about this name, I don't know. I have like this incredible fear of the dentist. And every time I see that name, all I can think of is root canal. So anyway, it always scares me just to say extraction of roots. But anyway, yuck. All right. So extraction of roots. Now let's take a look at our quadratic equation. Oops. I'm jumping ahead to the end of the course when we do exponentials. Okay, ax squared plus bx plus c equals 0. That's one type of quadratic equation. If b equals 0, then this whole middle term just goes away. So you're going to have some number multiplying x squared. It could be 1x squared, 2x squared. And you're going to have a constant. And the constant's either on the left side or the right side. So the quadratic equation could look like this, or it could look like this. Okay? Whatever c is. All right? Now, notice, if one of your terms is missing, the bx, the middle term is missing, that says, hey, there's a special method to solve this equation. That's this method, extraction of roots. Okay, so I want to not do this one first. I want to do this one. Now, if I could possibly convince you, not to do what 80% of algebra students do, I would do anything. I'd get up here and I'd do a song and a dance on the table and you could laugh at me. I mean, really, I would beg you, like anything. I couldn't give you a lot of money because as a community college teacher, you don't make a lot of money. A passing grade for the rest of your life. Maybe if I could convince everybody to do this. What's the tendency when you see an equation like that? What's your tendency? Yep, Moshe? Yeah, and that's going to get you in trouble. Let me show you why. You're going to do this. Oh, someone's already stole my punchline. Don't forget the negative. The negative what? Don't forget the negative square root. Okay? When you do this, you set yourself up for missing half of your solution set. Because when you see this, you only write x. And we went over this earlier in the year. The definition of the square root of x squared is not x, it's this. Because the thing you have here could be a positive number and square it, or a negative number and square it. So in order to ensure that you write the proper answer here, you have to put in an absolute value because we know square root's always got to be positive, and that's why we have to write that. So unfortunately, all those years you were practicing this before coming to this class, your teacher allowed you to write x here, which is really not true. It should be So they allowed you to write x and just said, make sure you do plus and minus 5. But when you see that, it just says the positive square root of 25. You're not going to remember to put the plus and minus. So for all of your life, you've been getting probably half your answer. Okay? So what can I do to undo that? Well, I can encourage you. I can keep doing lots of problems. You can keep doing lots of problems. You know, I can just say, you know, really, if you do it this way, you won't forget. So if you do this, which is really the square root of x squared, and what that really says is just the positive square root of 25, the minute you write this, now you know there's two things you can put in there, right? Two numbers you can put in here whose absolute value is 5. What are those two numbers? 5 and negative 5. So when you have an absolute value equation, there's two possibilities. X could be 5 or x could be negative 5. So if we had teachers just simply make us do this step, we never would get this wrong. But I can't force you to do it, and I don't know if I've even convinced you. The other way that I think may convince you that maybe you'd have less problems with is this. Set this equal to 0, which is what you do to solve your quadratic equation. And now the conjugates come back into play. No, I changed the problem for a minute, Marco, up here. See, I made a little change. We're going to come back to that one in a minute. So this is what Marissa was talking about, right? This is the difference between two perfect squares. You can factor these in your sleep because they're conjugates, x plus 5, x minus 5, right? Easy to factor. So something times something equals 0. So we call this the zero principal factor. You set each factor equal to 0. Notice each factor, so you got two different answers here. And this way is another guarantee that you won't miss one of those. But no matter what I've done, my 35 years of being here, I'm always going to get the students that they don't want to do the absolute value, they don't want to factor, and they put this square root and they forget the minus. And that's what I'm saying. I wish there was some way I had some magic bullet to have this be so that you wouldn't forget it. But I don't. That's the best I can do. All right. So let's look at this one that's here. X squared equals negative 25. So if I throw the 25, the negative, if I add 25 to both sides, I get x squared plus 25 equals 0. And before now, you would say, no can do. I can't do this, but now we can. This is x plus 5i, x minus 5i, back to the conjugate idea I used just a minute ago right here with the x squared minus 25. So here are your two factors, x plus 5i equals 0, and x minus 5i equals 0. So x equals negative 5i here, and x equals positive 5i here. So there are your two answers, plus and minus. Just like here we had plus and minus 5. Okay. Because in order to multiply, this is the sum of perfect squares here, Moshe. I know that I can't do x plus 5 and x minus 5. This is the situation we just looked at a minute ago. We can do a plus and a minus as long as we have 5i and 5i. The other thing, huh? No, because it's part of, that's the answer. And another way to look at this is if you kept it just as it says and you want to do what Moshe said, which is square root both sides. See, now we can take the square root of negative 25. It's 5i, but you got to remember it's plus and minus 5i, not just 5i, because this is absolute value right here. Nope. You're going to have, except for when you have a perfect square, when you solve a quadratic equation, you'll always get two answers, two different solutions. Sam?
So on the left, you have absolute value of x equal to 5i, and you have x is equal to plus or minus 5i.
Yeah.
Would either be acceptable for an answer written down?
Yep. No, you have to go from here to here. You have your solution set is 2 answers. So your solution set, when you write it in my math lab, will always look like this. You put both of them in, and you always put your smallest solution before your largest solution. Okay. All right, this one, let me put this on a new page. -2 times x minus 7 squared equals -20. Is that what it says on there? Okay. Now, students usually, when they see this, they usually do this the long way. They take x minus 7 and they multiply it times itself, and they get this long thing on the left side, and they create a lot of work for themselves. But what you need to recognize is you've got a perfect square here, just like we did a minute ago. So you got a perfect square on one side of your equation. So keep that by itself and get rid of any number that's multiplying it by dividing it on both sides, like that. So you get x minus 7 squared equals 10. Now when you square root both sides, you extract the roots. You get x minus 7 on this side, and you get plus or minus the square root of 10 on that side. So again, remember, the step that's being left out is this should say the absolute value of x minus 7 equals the square root of 10. So that means the thing inside here can be either positive square root of 10 or negative square root of 10. And then to solve for x, you just add 7 to both sides, and now that's starting to look like your quadratic formula. So the answer here is 7 plus square root of 10 and 7 minus square root of 10. Those are your two answers. So this is called extraction of roots. Like I said, you could have squared out 7 the long way, but you would have needed the quadratic formula to solve it, which we have to cover.
So what happens if you can't divide nicely by divide by -2 on both sides? Worked out. What if you can't do that?
Well, you're going to just get fraction of it. If you have like -3, you got negative. It's just not as nice.
It doesn't matter what's on either side.
Okay, so the second method is called, we've already used this, the zero product principle or property, which is if you can take your equation and write it as 2 factors, you can factor it, then each factor equals 0, you solve each factor for the value that makes it 0. So in other words, that's why we had to do a little practice with factor. X squared plus 11x plus 24 equals 0. Notice the key here, setting everything equal to 0. So the first step is to set it to 0. Now you say to yourself, what factors of 24 add up to 11? What are the factors of 24 that add up to 11? 8 and 3. 8 times 3 gives you 24. And they add 8 and 3 add up to 11. So these are pretty straightforward. Once you have that multiplication problem, you say, hey, when does x plus 8 equal 0? That's just a little baby. Your equation solved. Say, hey, when does x plus 3 equal 0? X equals 3. So the yeah, if you were writing this in a solution set, my math lab put the smallest solution, which is -8 plus. Now notice this only works, that's why I have this in bold, when you have 0 on that side. So you've got to make sure you have 0 on one side, because this property won't work. If I said, give me 2 numbers that equal 4, this is infinite. So putting 7-year equation equals 0. All right, so let's hit the quadratic formula, and then I can give you some time to work on these yourself. So the third method, which is the most useful of the 3, because if we solve this equation for x, just like this, I can solve this equation using a technique called the square. This is what the answer looks like with all of the coefficients A, B, and C. So it's a formula that works all the time, which is great. So unfortunately, my little link here doesn't work anymore. And it's a musical tune to a song that some of you probably know called This is the actual song. But we're going to use the melody for to sing the quadratic formula. So you'll never forget it. So I'm going to start. You can listen to it once. So here it goes. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. Ready? X equals negative b plus or minus the square root b squared minus 4ac all over 2a. One more time. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There's always a student that won't sing that say to the next class, I'm going to get that tune out of my head. What's really great is how do we remember things when we're really young? Think how we remember the alphabet. Why did we remember the alphabet? Because we put it to a melody. And my daughter has a very long hyphenated last name, so I use this idea of knowing, putting names, things you're trying to remember to melodies. So sometimes, I mean, think of all the songs we know by heart, right? It's amazing. They're just a tune and remembering something. So there's really never a need to have this formula now test. All right, so let's do it here. What's A, B, and C here going to be? A, B, and C, and then I'll let you tear these class activities. What's A, B? 1, B is negative 6, and C is negative 7. Here we go. X equals negative B plus or minus the square root of B squared minus 4AC. Can't do the all over anymore. All over 2. Yes, let me point out a couple of things while you're frantically writing this down and using your calculators. B is a negative number. It must be in parentheses. So check your notes, and if you have dash 6 squared without the parentheses, that's not going to give you 36. It's going to give you negative. Anytime A or C is negative, I would suggest you put brackets around that all the time. So x equals the opposite of negative 6 is a positive 6. Negative 6 times negative 6 is 36. Subtract a negative 28 over 2. And now subtracting a negative 28 becomes a positive adding 28. 6 plus 28 over 2. And 6 plus or minus the square root of 64 over 2. That's what you like to see. 6 plus, now x equals plus or minus 8 over 2. So what are your two answers? 6 plus 8 over 2, which is 7. 6 minus 8 over 2, which is negative. Negative. So you have two answers. X equals 7. X equals negative 1. Writing it. Now, if I were doing this problem, I would have never done it. Because I look back here, I would have just mapped it out. X minus 7, x plus 1. We've taken maybe less than a minute. So anytime you use your quadratic and your answers are rational numbers, that means you could have factored your original equation. You went through a lot of this. Most people feel really fine in things in formulas and get not afraid of the shortcuts. They can add and subtract easily, so it's not. So make sure you know how to do these without a calculator, because there'll be times when I tell you you can't use a calculator. It's not a multiply and subtract. So if you're dependent on your calculator, listening to me, try to do
So you've got plenty of class activities to keep you busy. Any questions on anything? Just put your flag up and I'll round up. If you don't mind, get a flag out of the cabinet.